Thank you so much. So we are now going to kick off data-driven discovery. And the idea of this session is that we could explore how large or carefully curated data sets or new advances in data science can lead to new discoveries. And the idea is to think about discoveries within and beyond academic research. So we have a great lineup of KIPAC alumni speakers for you that are doing awesome things in very different realms. And we'll start with Kyle Story, who is the climate solutions strategist at Muon Space, which is a remote sensing startup down the road in Mountain View. Kyle earned his PhD from the University of Chicago and then came to KIPAC as a Cobley postdoctoral fellow. Before joining Muon Space, Kyle worked at Descartes Labs on geospatial analysis with machine learning. And today we are fortunate to hear from him about operational climate solutions. So with that, we'll hand things over to you. Take it away.
Okay, thank you. Check one, check two. Is that working? And is there a laser on? Just not gonna work. Okay, that's fine. Let me just make sure this works. Okay, great. Thank you so much for the opportunity to come back to KIPAC and speak with you. It's really exciting to be here and to participate and share in the 20th anniversary. I want to spend this time telling you a little bit about what my journey and what I've been thinking about for the past 6 years since I left KIPAC. So one slide on me, everything else not on me. So my path from cosmology to climate at KIPAC, that's me on the South Pole Telescope in Antarctica. Spent my time thinking about the cosmic microwave backgrounds, gravitational lensing in particular, B modes. This is an analysis that we did, Kimmy Wu here while I was at KIPAC. Really fun and exciting work. And then I left KIPAC to join Descartes Labs to work on climate. So Descartes Labs is a startup company that has built a geospatial analysis platform, geospatial meaning imagery of the Earth from satellites. And so I worked on machine learning as a modeler, as a team lead. And this is an example of an analysis that we did to map all the solar panels in the world using machine learning on satellite imagery. And then helped establish the sustainability team and build out some deforestation work and other products I'll mention briefly in this talk. And after 5 years, moved on to Muon Space, where I've currently been for about 1.5 years. And I've moved up the value chain a little bit. And Muon Space, we're building new data sets. So not just analyzing what's available, but recognizing that there's quite a bit of critical data, new data that will be required in order to build climate solutions. And so at Muon Space, in this picture here, you can actually see our first satellite being released into orbit from the SpaceX transporter. And at Muon Space, I've also moved from technical work more into the strategy and defining what we should be building in the first place. So I spend my time, instead of thinking about code in the last debugging error, I now spend most of my time thinking about how do we construct holistic climate solutions? What products do we need to build in order for those to be actually used by end users? And then pushing all the way into the business models of how do we put these solutions into the real world in a sustainable way that will actually drive the change that we need. Enough about me, more about the world. So the world is in a climate crisis. I don't think anybody in this audience needs a reminder of that. These are a few examples from my work. On the left, this is wildfires. Well, I'll spend a lot of my talk today talking. This is the campfire from 2018, showing visible imagery in the top and then infrared imagery in the bottom where you can see the heat. The pink there is a machine learning model that I built while at Descartes Labs that shows building footprints. So you can actually see the heat sweeping through the city of Paradise in that image. In the middle, these are fracking well pads shown down here in the Permian Basin in Texas. This is just one snapshot of what the fracking energy boom in Texas looks like. And there's a critical need both to draw down on the emissions from oil and gas, but also direct emissions from burning it, but also the fugitive emissions from methane in particular associated with fracking. I won't get much time to spend on that in the talk Ask Me After. And then lastly here, this is a snapshot from the east coast of Borneo in Indonesia. And you can see by eye quite clearly the areas that have been deforested in order to clear land for palm, particularly for mining and a number of other human-driven needs for that land, there is a huge need for improvements in data-driven discovery, but then also operational solutions to bring into balance how we use land across the globe. I'll touch on that one briefly a little bit in this talk, but again, bother me afterwards about it. So just to set the context, in 2018, the IPCC, the International Climate Report, released that we had approximately 12 years based on extensive modeling before dangerous levels of CO2 were locked in. It's 2023. Emissions continue to rise. And this is what that looks like. So this is from the 2018 around 2018 IPCC report. The x-axis is time, obviously. The y-axis is total global emissions of carbon dioxide. Those emissions have continued to rise up through here. I think this plot stops in 2018. They've started to level off a little bit, but have continued to rise today. And these are when I say climate scenarios or paths, these are the paths of total emissions that we need to follow in order to keep the climate on a stable path. And we need an entire regime change in emissions, or else we will lock in dangerous levels of emissions. And what that requires is operational solutions in the real world that are driving real meaningful impact and reduction in emissions. So the number to keep in mind is approximately 50 billion metric tons of CO2 are released into the atmosphere each year. That number needs to go to 0 on net. Not 5, not 10, 0. And actually will likely need to go below 0 in order to recover from many of the emissions that we have put into the atmosphere over the past 100 years. And so the important thing is the total amount of carbon dioxide in the atmosphere. This means we need a complete change in the global economy. And so that is what I'm going to be talking about, one small component of that. But when I say operational climate solutions, I mean targeting these numbers. So I'm going to tell you a story about some of the things I have done that did not work. And we'll start there. So I left to work on climate change. Great, we're going to go work on climate change. Wildfires are a problem. What can we do about it? Well, I'm at Descartes Labs. Me and the rest of my colleagues there, we have access to a ton of satellite imagery. Let's dig around in the data-driven discovery. Let's see what we can find. Oh, great. There's satellites that, like the GOES satellite, that are taking a picture of the Earth every 5 minutes. Amazing. What can we do with that? Well, we can see wildfires. There are papers published showing that you can see wildfires. You can see the infrared emissions from those wildfires in GOES satellites. Great. Every 5 minutes, let's build an early warning system. So we set out to do that. We built, mostly my other colleagues have participated, but did not lead this work. And we were able to show that we could publish alerts of new wildfire detections within 10 minutes of the picture being taken on the satellite. So picture from satellite, data coming down to the ground, going to data processing centers, running algorithms, having alert reported in 10 minutes. And this is showing an analysis using historical data to show when we would have detected a wildfire in New Mexico, Arizona and New Mexico using that system. So boom, incredible technology, really amazing capability. And one thing that we kind of knew going in is most people don't want data. Most people don't have the bandwidth or capacity to be able to plow through data. They want insights, right? They want you to tell you, just process that all for me, give me the wildfire alert. So that's what we were doing. So we worked with the LA Times to incorporate the early wildfire detections into a dashboard in the LA Times. Here you can see on Twitter that this particular fire had not yet been identified and published by the wildfire response agencies, but it was already on the Descartes maps. Amazing, we're gonna save the world. This is great. So then we waited and we waited. Crickets. No change, no impact, no reduction of 50 million tons, 50 billion tons, order of magnitude. So what went wrong? What did we do wrong? We gave them insights. We didn't just give them data. We produced wildfire alerts. I think what I've come to realize is that people don't want insights. They want their problems solved. They don't have time. They don't have the money to dig through this, even if they have the ability to really want to just solve problems, right? So the rest of this talk is how do you get to solving problems? the issue with what we had built at Descartes Labs is that early detection isn't the main problem in the US. So we're solving the wrong problem. What you see here is a map of all of the airplanes in green, all of the ground camera stations in California in blue, and then people just on their phones calling 911. Early detection is actually pretty well under control. This is not true globally, but this is true for California and the US. Early detections is not the key problem. So I will return to what we are working on in at Neon Space to try to dig into that a little bit. I want to set out a little bit, a few principles for how do we actually get to solving problems, and then show the wildfire example, what we're doing at Neon Space of that in practice. A key thing is we need to understand decision makers' needs. This quote I love: if you want to be a force for justice, you need to get proximate to those who are suffering. And so so for us, that means you need to talk to the people who are actually using the data to make decisions, understand those problems, and then build the technology to solve those problems. Starting from the technology rarely works. So now I'm going to show a bit of an example of how we're trying to do that at Neon Space. We are working on wildfires, and here we are building a new constellation of data to drive operational decision making and provide early detection and monitoring of wildfires. The program goals are to improve early interventions, build resilience in communities, and eventually develop a much healthier approach to ecosystems. And the outcome that we are seeking is a healthy fire-adapted ecosystem and resilient fire-prone communities. This is a collaboration. So Neon Space, it was catalyzed by the Environmental Defense Fund. Neon Space is the technical developer, and we're working closely with them. We work closely with the philanthropic community who have funding to be able to get early stage ideas off the ground and then have a long-term vision and long timelines for what they're trying to drive. And then the point that I just made, through this program, we've already conducted over 200 interviews with stakeholders in the wildfire ecosystem as the starting point. And then using that base of information for what exists now and what solutions will actually be needed to change the state of the art as the basis for designing the technology and the data system. And from this, my current understanding of the critical problems are, it's not early detection, but initial assessment is critical to be able to escalate response where necessary quickly in order to save lives. Frontline fire safety, so having much better situational awareness for the people with pickaxes on the front line digging the trenches. And then more long-term, a fundamental shift from a suppression mindset to including good fire on the landscape, and that is a much longer project. And the key users here are frontline responders, incident commanders, and then on the relating to data-driven discovery, scientists and modelers who need to push the state of the art of what we understand and how to develop these solutions that will eventually be implemented. So the second point that I want to make is an operational solution requires much more than just the data. Data is a critical component, but it is one piece that fits into a whole solution. And let me speak a bit about that and then show wildfires as an example. I was supposed to remove that slide. So I'm working in satellite space. I have lots of access to geospatial data. Great, that's a circle. That needs to be combined with other data sets. You could take this into other contexts. We need all kinds of different data. One data set is usually not enough. That is critical to incorporate that with domain context or experts, like those 200 interviews to understand exactly how that data fits into the workflow of somebody who's trying to make a decision. That's not enough. So that drives the insights, but in order for those insights to actually solve somebody's problem, they need to get served into somebody's workflow. That usually goes through an application or a service. And only when you get to the decision of the action is this whole system valuable. And if this whole system doesn't exist, then you kind of build up latent value, but it's only until you can take this action that we can actually start targeting that 50 billion metric tons. Kind of pedantic example, but when I left this morning, should I grab a raincoat? I don't know, but that's the decision I need to make. So under the hood, there's satellites, there's weather stations, they run through numerical weather prediction models. That's not enough. They then get served through a weather forecasting app, so I can pick up my phone and in half a second see whether or not I need to take a rain jacket. This is what it means, getting it down to that simple decision-making process to drive operational solutions. So here I want to show a slightly different but related how this relates to data-driven discovery and the fact that there's kind of a path for the development of new technology and where data fits in. So initially, there's a critical role for data-driven discovery in understanding, discovering what's measurable, building up the foundational knowledge. Then that knowledge can be put into pilot programs to show that it's possible to build an operational solution. And only then does it get pushed out to implementing at scale, where you have to get all the way to here in order to actually drive impact. So I'll talk through the wildfire use case. In the interest of time, I'll have to flash through the other use cases, but we'll do wildfires and then open for questions. Good. So we are at Muon Space, as I said, building a wildfire constellation. From those user interviews, this is the baseline attributes for the system that we've developed. So it's a wildfire focused system, building data from the user needs, not the other way around. That means picking the right cameras, picking the right spatial resolution, the right cadence. The data must be delivered in real time to drive those operational decisions, and then it must be integrated into those applications for the end users so they actually can use it to make their decisions and solve their problems. As a high-level concept of operations, that's the Muon satellite. That's what the box that's in space right now looks like. It will be observing wildfires, streaming that data through high-speed downlinks down to the ground, and then processed through a variety of modeling and then distributed out to the frontline incident commanders, and then also supporting scientists and modelers. In order to get this constellation, we are planning on a constellation of 52 satellites that will provide 20-minute revisit every hour on Earth. And that number has been based on those interviews with stakeholders to understand what cadence is necessary for their decisions. Ask me later about the camera. This is an infrared system that will see the heat from wildfires, but also have a good frequency range that allows a pretty holistic understanding of the landscape. And then quite a bit of work on the near real-time data downlink to get that down. This is kind of what that's going to look like. So up on the left is a simulation of a wildfire perimeter. See 10 kilometers across. And this is why this new data system is necessary. The bottom of the existing satellites, this is the one we built the wildfire alert system off of, GOES. This is the VIIRS satellite. It has pretty reasonable spatial resolution, but it's only every 12 hours. So it's good for situational awareness. But if you're on the front lines and you need to know if a spark just started a fire over in front of you and you need to leave, it's not sufficient for operational decision-making, and that's what we're building here. So this is kind of what that looks like now running this as a video. We'll be taking images of this and then getting it down to the frontline responders every 15 minutes. And as you can see, in VIIRS, you don't even know that this fire has started yet. And in GOES, it's just too coarse to be actionable. And then finally on this, the data products that we'll be producing from this, the basic ones are fire perimeters, radiative power, so the amount of heat coming from that fire. That tells you where on the front line to respond to, and then also what ecosystem impacts to expect. And then rate of spread, that's a very important one for how is that fire spreading through time. And again, provided through the decision support systems that are existent right now. So relating this back to that high abstract graph that I put up before, there is a key role for data-driven discovery in wildfires in this example. Down on the R&D side, what does good fire look like? What are the metrics? How do you measure and monitor whether a fire is damaging or positive? How do you relate that to emissions? Fires emit significant emissions against that 50 billion metric tons number. Better model predictions for the spread of wildfires. In the pilot programs area, we've shown that we can see wildfires from satellites, but as I said, the data aren't sufficient to drive operational decision-making. And predictive models are pretty manual right now. It's a huge opportunity to improve and automate those. And all this will need to be implemented at scale and in order to actually drive impact. So I'm out of time to talk about the other solutions. So we can catch me offline, talk about land use change, and then some of the cool stuff that I did at Descartes Labs here, building models that are monitoring for deforestation in real time. The key transition is relating that to carbon now, not just deforestation, but building it into a full accounting of the carbon in land use, and then reporting and creating the incentive structure that drives the incentives to actually carry out positive practices in land use. And yeah, of course. And then all of that necessarily relies on regulation, but it's all tied together. I did some really interesting work on renewable energy. This is the mapping of all the solar panels in the world. This, in my mind, really fits down here on the R&D side. And so in order to turn this into something operational, a lot more work needs to be done to understand what decisions this would actually drive and then build the systems to drive those decisions. Methane emissions, I'm out of time, but there's a ton of really interesting work here along that whole spectrum of fundamental understanding all the way up to implementing solutions. And the key is that we need broad area monitoring that is tied to actual emissions in order to get a handle on and regulate and control methane. So my last wrap up slides here, I think one point I want to make is that just waiting for the market to solve climate isn't going to work. If we wait for pure market dynamics, we will continue to burn hydrocarbons as long as it's economical, and the world will burn. I think a good analogy to this is slavery. We actually chose to end slavery while it was still profitable. And so as humans, we need to make a choice. So I'll leave the last 2 points up here and pause there for any questions.
Fantastic. All right, please raise your hand in the room or online if you have questions for Kyle. I see one down here.
Thanks, very interesting. 2 questions. Who is funding it and what does it have to do with muons?
Yeah, very little to do with muons. That was just a creative name from the founder. And the funding is the whole story. So like I could talk to you for hours about how to fund climate solutions. For this one specifically, the concept is to get the demonstration principle off the ground with substantial philanthropic funding, tens of millions of dollars in philanthropic funding, show what those measurements can do, and in the process build a broad base of funding support, likely from government, philanthropic, and some commercial interests, so that you can provide these data all the way down to end users and the frontline responders at a low cost or free, so they can actually implement and use those data, but they're not going to be the ones who are going to support the business model. So that's the concept, but there's a lot of details under that.
Yeah, so thanks, Kyle.
Yeah.
That was great. Can you talk a little bit about whether at Muon you're also thinking about wildfire prevention through forest management? Like, can data be used to maybe identify where forest management would really help and where the good fires could be utilized more effectively? Yeah,
it's a strong and important point of the program. I focus here on the initial response to fires because that is one of the places where the data can be actionable immediately and drive immediate outcomes. Over the longer term, there's a whole program of better modeling wildfire risk. That's still kind of seasonal. Better understanding good fires, and so we can incorporate good fires over many years to decades as a management practice, and then having the right data to be able to implement effective management programs. So you know when to put out a fire, when not to, where to run controlled burns in a safe way, whether or not the landscape is in a healthy state or not, and then the actions to take against that. So yeah, there's a strong program there that this will be a component of, but we'll rely on a whole other set of data as well. Yes.
All right, Elise and then Risa.
Cool. Yeah, this is really cool. And I really appreciate your point of like needing to make this connection between the people doing the analysis and then actually getting that to end users. And I was just wondering, like, having worked in this space, do you have any insights into kind of how we build those connections more robustly?
Yeah, I think one of it is just getting out there. So I speak from personal experience, being, coming up through physics and as a physicist, coming up building lots of code. Even just for me, it does not come naturally to go talk to people. And so I've pushed very hard at the personal level because I recognize the importance of just as like us data-driven technologists, understanding the importance of stepping out of our comfort zone and interacting with the rest of the community. So that's one. And then I think having the overall goals in mind, so having impact-driven goals in mind, and then understanding the components that need to fit into that as a strategy, and then executing that strategy. And so saying, okay, this will require policy. So let's see, our CEO was in Washington, D.C. several times over the past year. We're up in Sacramento talking to legislatures. This requires the rest of the world. We will be engaging or already engaging Canada, Australia, and we'll be looking at ways to spread that impact to stakeholders in the rest of the world. And then just starting from what outcome are you trying to drive, working backwards to the roadmap or the steps, and then just executing against those. There's no simple answer, but it's just getting out there and doing it.
This is really beautiful talk and exciting work that you're doing. On the fire work specifically and transitioning to this regime of good fire, you know, there are some parts of the world where Indigenous people have long practices on this. Are you connecting with those leaders and thinking about how to integrate that experience?
Yes, absolutely. Yeah, the Indigenous world is far ahead of the Western world on good fire practices and have centuries of real lived experience in doing that extremely effectively. And so, yes, we are connecting with those. The work with big philanthropy is also critical in that because they can have longer timelines in terms of the impact that they're trying to drive. And so, yes, we are working closely with Indigenous communities, both in the US and then globally as well, to incorporate those practices. And there are real challenges around, especially as you get into policy and implementation, on even if an Indigenous group knows the right things to do, having a cultural burning of an area be something that can fit into, permitting for controlled burning, that kind of thing. So absolutely a critical part of the conversation, part of this conversation, but a lot of work to make sure that it's incorporated well, but it's absolutely critical. Thanks for making that point.
Hey, Kyle, great talk in the back here. I just had a quick question. Maybe I missed this, but did you talk about at all how you're how you're feeding data in for your predictions for these wildfire stuff? And are you doing anything like in real time to get some feedback to directly address, how things would be changing over time?
Yeah. So is this a question about how we're feeding data into the end users, or a technical question about how we're feeding data into like what type of modeling?
Your prediction model, yeah.
Frame.
Like how you're feeding into that.
Yeah. So a key area of growth here will be, so there's real-time situational awareness, which you can do with these basic products. Where is the fire now? And then based on the last snapshots every 20 minutes, how is it going to spread, what I showed there. There's a whole new regime of, okay, let's make predictions for the next 1, 3, 12, 24 hours for how the fire is going to spread. Quite a bit of work has been done on that, and the community is somewhat split on whether the models are good enough and we just need better data, or if there's fundamental improvements. I'm sure both are true. So I think these data will be a critical improvement in the predictive fire behavior side in two aspects. One, as ground truth, to actually be able to see how a fire grew and progressed over time. That can then be built into model training, machine learning, or even standard models. And then much more frequently, persistently and frequently updated data to run those models at inference time. So right now you run those models every 12 hours, and that is the prediction that sits for the incident action plan and folks who are making decisions until you get another pass of data. Now we'll be able to update those data, just like weather models that are updated frequently will now be, even with existing models or improved models, we'll be able to actually update those on better initial conditions.
Thank you.
All right, that was okay, one last question.
Taking you back a bit. So carbon capture.
Yep.
Does it make any sense? Is it, do you have any solutions? Do you work on that?
Yep. There is virtually no way we will meet these carbon reduction pathways to stay on a path to a stable world without substantial removal of carbon from the atmosphere. I think that is a fact. So either world is hotter than we want it, or we figure out carbon capture. Now and I'll try to keep this short, but catch me offline. There's a significant amount of carbon capture that can happen in the natural ecosystem. Land use change can provide about 30% of that reduction potential. A lot of that comes from restoring natural ecosystems to capture. It won't be enough alone is a key component. It won't be enough alone. And so I truly hope that the direct capture, directly drawing from the atmosphere, that we are able to continue to improve that technology. Right now, demonstrations are out. We can pull a carbon out of the atmosphere. It's 1 to 2 orders of magnitude too expensive to make sense. And so with that, it's all about cost. That cost needs to get down to the point where you can scale it by several orders of magnitude up. Yep. In terms of the amount of carbon that you're pulling down. And so we do not have that technology solution in hand yet. A number of places are working on it. It will be a critical component.
Fantastic. And let's keep this conversation going. Let's thank Kyle again.